Welcome everyone. Let's look at what we call Faraday's laws of electrolysis. These laws are quite very important because we use them to calculate the mass of the substance deposited or liberated. We also look at the charges. Okay, it helps us in determining the moles of electrons that are required to deposit a certain amount of substance and things like that. So there are basically two laws that we are going to look at, and with these two laws we shall be in position to basically carry out a number of calculations in relation to what I've talked about, the mass of substances, whether deposited or the volume of gas evolved. These laws can help us in those calculations. So let's basically start. We already know that in electrolysis we pass electricity, and that electricity that we pass makes some reactions to happen. And actually we say that passing electricity or electric current through an electrolyte, you're going to have reactions happening. These reactions are not spontaneous. Okay, so that means that the amount of electricity that you pass will influence the chemical reaction that is going to take place at the electrodes or within the electrolyte. Okay, so that the amount that you pass is also directly related to the time for which you pass this electricity. Okay, that is also very important. And then the last thing that we can talk about here is about the charge that is on the ions that are part of the electrolyte. Okay, the electrolyte has these ions which are free in the electrolyte. That is, they move. Okay, they move freely. Okay, they move from the positive ones move to the negative ones, and then the negative one moves to the positive electrode. Okay, you remember that quite well. So let's basically start this presentation and look at the first law of Faraday. Okay, the first law of Faraday. What does it state? That first law states that the mass of a substance produced or consumed at an electrode during electrolysis is directly proportional to the quantity of electricity passed. The quantity of electricity passed. That means that when we pass this electricity into this electrolyte, you're going to have substances which are going to be deposited. For example, if you have copper ions as one of the ions in the electrolyte, these ions can get discharged. Okay, so you will have electrons. It basically gets reduced. It gets reduced for you to have copper solid. Okay, now the charges needs to balance. So you have positive 2 here. You need to balance with this 0 charge here. You put a 2 here, such that this 2 and this 2 here cancel out. Okay, so you have the copper ions being converted into copper solid, right? Yes. So that is what this is to say that you're going to have copper being deposited. Copper being deposited. This is to say that the ions are losing the charge and then they are being deposited usually at the cathode. Okay, at the cathode. That is where you're going to have this reduction happening. Okay, so the mass of this copper, which is actually being deposited, okay, deposited or produced, is equal to the amount of electricity that is being passed. Okay, so therefore, if you plot a graph of the amount of copper deposited versus the amount of electricity here, you will have a straight line, just like this one. When you have a straight line like that in a graph, it means the two quantities are directly proportional. Okay, so that means when you increase electricity, you increase the amount being deposited. That's what it means. So that is Faraday's first law of electrolysis. So mathematically, we express that using Q to represent the quantity of electricity, and this quantity of electricity is in the units called coulombs. Okay? So this is directly proportional to electric current being passed, and the electric current is given by IT. The I is the electric current, which is in amperes, and then the T is the time, which is in seconds. So meaning that for any calculations that we shall face, we will need to have the time in seconds, and we will need to have the current in amperes, and we will need to have the quantity of electricity in coulombs. Are we together? Okay, I guess that is so far okay. We're moving on well there. So further explanations. We have what we call Faraday's constant. And Faraday's constant is basically about the amount of electricity that you actually need to liberate or to produce 1 mole of an element. Okay, and usually this is actually directly proportional to the charge on its ion. So what we are basically saying here is that 1 mole of electricity is equivalent to basically what we call 1 Faraday. And 1 Faraday can be abbreviated as 1F here. And that 1F is actually equal to, that is 96,500 coulombs. Okay, so the amount of electricity, or the moles of electricity required to liberate 1 mole of an element is proportional to the charges on its ion. This is basically related to the second law that we are going to look at briefly. But what for now you need to know is that 1 Faraday is equal to 96,500 coulombs. I will see why that is quite very important there. So the coulomb is the unit for the electric charge, and this is basically the international unit for electric charge. And if you want its definition, is the amount of electric charge that flows through a conductor when a current of 1 ampere flows through it for 1 second. So the unit for electric charge is coulombs, right? Yes. So if we are to define coulomb, we are saying that it is the amount of electric charge that flows through a conductor when electric current of 1 ampere flows for 1 second. Okay, yes, so that is what we call a coulomb. Now let's move forward. So Faraday's constant, we talked about this earlier on. We hinted on it, but let's basically get it more here. We are saying that the quantity of electric charge carried by 1 mole of electrons is what we call Faraday's constant. Okay, is what we call Faraday's constant, and that constant is very important. It will always be provided to you on the question paper, so you don't need to memorize it, but at least you need to know what it stands for. Okay, so 1 mole of an electron has a charge, and that charge is what we call Faraday's constant. Okay, is what we call Faraday's constant, and that charge on 1 mole is actually this. It's 1.602 times 10 power negative 29, right? But you also need to remember that for 1 mole of electrons, you will have Avogadro's number of particles. That is, you will have 6.022 times 10 power 23 electrons. Okay, and therefore Faraday's constant is this number here. It's this one here. The charge on 1 mole of electrons is actually 96500. So 96,500 coulombs per mole. Okay, coulombs per mole. So let's look at the second law of Faraday's second law of electrolysis, which is that the mass or the number of moles of a substance deposited or liberated at an electrode during electrolysis is inversely, this is now different from the other one, is inversely proportional to the charge on its ion. That means that you don't have both of them increasing. When you have the number of moles or the mass increasing, the charge on the ion decreases. That is what we mean by inverse relationship. So inversely proportional. So for example, monovalent ions. For monovalent ions, 1 mole of electron is required to deposit 1 mole of that element. But for what we call divalent ions, you need 2 moles of the electrons to deposit 1 mole of that element. So we are saying that, for example, copper, for copper to be deposited to form this, you need electrons here, right? These electrons have to be 2 to balance out that charge, right? So you need 2 moles of the electrons to deposit 1 mole of the element copper. That's what it means. If I can write it again, for you to have copper converted into copper solid, you need to add electrons here. These electrons, the charges need to balance, so you put a 2 here. So you need 2 electrons to deposit 1 mole. This is 1 mole of copper. Okay? And remember, the charge on 1 mole of electrons is 96500, right? You remember that? These are columns. Remember that. So let's do some calculations. I'm quite sure that they are not very complicated. You just need to make sure that you follow up the calculations. So calculate the quantity of electricity passed when a current of 4 amperes, the A is ampere, right, is passed through an electrolyte for 45 minutes. So here, remember the formula. The quantity of electricity is equal to IT. And the I is the current, which is 4 amperes, times the time. The time is 46 minutes, but this 46 has to be converted to seconds. If you remember that statement I made earlier on, so you will have 45 times 60, because each minute, remember, 1 minute is equal to 60 seconds, right? That is why we are multiplying this here to get the time in seconds, right? So what do you get there? That answer is in coulombs, because it is the quantity of electricity. So let's do that quite here. Check here, see what we get. So you have 4 times 45 times 60. Yep. So you get 10,800. So that is the quantity of electricity in coulombs. Okay, so we move to the second question. A current of 0.5 amperes was passed through copper 2 sulfate solution for 3,860 seconds, and a mass of 0.64 grams of copper was deposited. Which electrode gained the mass? Okay, so basically here you need to know, for you to have copper, what type of reaction is that? For you to have copper being deposited, what type of reaction is that? I guess you're saying it is a reduction reaction. I guess that's what you're saying. What happens is that you have the copper ions getting electrons basically reduced, right? Getting reduced to form copper, which is solid here. These are aqueous to balance the charges. They have it at 2 there, right? Yes. So this is a reduction reaction, and reduction happens at the cathode. Oxidation happens at the anode, right? And that is the reaction happening there. So this is that it is happening at the cathode. Remember, the positively charged ions go to the cathode, and that is where you have preferential discharge. And in this case, the copper ions are getting discharged to form this copper, which is the one being deposited, right? So the second question is, how many coulombs are needed to deposit 1 mole of copper? So of course, we need to first understand the quantity of electricity passed, and then from there we can do the other calculations. So the quantity of electricity passed is equal to IT, and here you have 0.5 amperes times. This time the time is given in seconds, so you don't need to multiply or to convert it further. Okay, so let's do that and see what we have in there. Yes, so let's see what we have there. So you have 0.5 times 386. You get, I hope this is what you have. It's 1093 columns. Okay, that's what you have there. That is what you have there. Remember from our calculation, not from our calculation, from our previous statement, we said that Faraday's constant relates to the amount of charge on 1 mole of electrons on an element, right? So you have, if I'm to rephrase that statement, you have 1 mole of electrons has a charge of 9 coulombs, right? Now, for 2 moles, if basically this, it will be that times 2. For 2 moles of electrons, 2 moles of electrons, it will be 9 by that times 2, right? So why are we looking at 2? Where is this 2 coming from? That 2 is coming from the fact that for you to liberate 1 mole of copper, you need 2 moles of electrons. That's why balancing the equation becomes very important. Okay? If you remember, if I go back here, you remember this statement here that 1 mole of copper to be deposited, you need 2 moles of electrons, right? That's where the statement is coming from. That's why we are looking at this part here. 2 moles of electrons of copper will give us, so let's multiply, will give us 1 mole. That question is quite straightforward. We even did need to have this. We actually didn't need to have that. So let's get that. 9650 times 2. So you actually get 19300 coulombs. This is what is needed there. Okay, so if we had a question that asked us to calculate the quantity of electricity passed, this is what could have been the answer. Okay, but from logical reasoning, like what we had earlier on, if we know that for copper ions, because the charge is 2, that means that you need 2 moles of electrons to produce 1 mole of the element copper. Then going straight forward here, you get that answer. Okay, but also you can still go with this approach. Let's try that out. So what we are saying with this first approach of first calculating the quantity of electricity, what we can actually do is we can say that means that our 9.3 this is giving us 0.64. Okay, that's what it is giving us, right? What columns can be able to give us? Remember, 1 mole of copper weighs 64, and you will have that figure. That is the relative atomic mass. You will have that figure on the periodic table, or that figure will always be given you just after the question, depending. Okay, so 1 mole is actually equal to 64. 1 mole of copper is equal to molar mass is equal to 64. So you want to find out this, which you actually don't know here. So this, you basically cross multiply, right? So you will have x equaling to 193 times 64 divided by 0.64 here. So let's see the answer that you get, whether it will remain the same. Let's see if the answer we get will remain the same. So 193 times 64. Okay, let me write it here. So you get 1,000. Is it 120? 123,520 divided by 0.6, 0.64, and divided by 0.64. So you actually get the same answer. You actually get the same answer. These are coulombs, right? With the C there. Okay, I hope that is quite clear with that example there. Okay, so you can use either approaches and still get the same answer out. So for a question on a current of 2 amperes, was passed through copper sulfate solution for 30 minutes, capturing the mass of copper deposited at the cathode. So you first calculate the amount of current, amount of electricity. You get 2 times 30 times 60, because the time has to be in seconds. So this will get 36, and then plus the 2 zeros. Okay, so what mass is this one deposit? So we need to first determine the number of moles. Okay, the number of moles that this electricity or this charge will actually deposit. Okay, so that's the next step. So how do we know that? We know that for copper, for copper ions to be deposited, you add 2 electrons there to give you copper solid, right? Yes. So what is the interpretation here is that you will have 2 moles, okay? 2 moles of electrons depositing 1 mole of copper. So remember, 1 mole of electrons having a charge of 9.6.500. Okay, that is 1 mole, right? Now, what about when you have 2 moles? Okay, 1 mole of electrons. So 2 moles, you basically just multiply that, right? So what do you get there? This is what you get. Okay, now you're having this charge here giving you 1 mole. What about this charge that we have passed? How many moles will it give you? You basically don't know. So you get that and say cross multiply, right? So we go to our calculation, 3600 divided by 193, the 3 zeros, so you get 0.018. You can add that 6. Okay, so these are the moles. Now convert these moles to mass. You know that 1 mole of copper, 1 mole of copper is equal to 64. So what about those moles? What about 0.0186 will be equal to what mass? So this will be a multiplication, right? So the mass will be 0.0186 times 64 . So you get 1.19 grams. This is the mass that you will get, that will be deposited, right? I hope that has been clear. So we move to the next example. Now this one has volume in it. Remember in our presentation earlier on, we talked about the volume, the ratio of oxygen and hydrogen being produced, and I did stress that it could be very important that you understand these ratios because they can be of implication in calculations. And this is one of the areas where that basically comes in. So we are passing an electric current of 5 amperes through sulfuric acid, dilute sulfuric acid, okay? And you will have oxygen produced and hydrogen being produced in electrolysis of dilute sulfuric acid. They are saying calculate the volume of hydrogen gas being produced. Remember, this is usually provided in bracket that 1 mole of a gas at standard temperature and pressure, which is 22.4 liters. Okay, so let's go on with this calculation. What is happening in this electrolysis? How are we producing the hydrogen? That's the first thing I think you need to first understand. So, what ions are present in electrolysis of sulfuric acid? Since it is dilute, you have water there, and then you also have the ions from sulfuric acid, right? So let's start with the ions from sulfuric acid. So you basically have sulfuric acid, which is aqueous, giving you hydrogen ions, aqueous, plus the sulfate ions here. This is minus, right? So you need to balance it, right? Yes. So, and then you have the water, liquid, giving us the hydrogen ions plus the hydroxyl ion, right? This is all aqueous, right? So what we are having is that these hydrogen ions are the ones that get discharged. Hydrogen ions aqueous get discharged to give us hydrogen. So electron, okay? So to balance this hydrogen is 2, we put there. So to balance this, you need to have 2 there. So you have 2 moles of electrons now giving us 1 mole of hydrogen gas. So that information there is king. Eh? That information is king. It's very good information. So let's move forward. Now, what do we need to do? We'll calculate the amount of electricity as usual, IT. So you have 5 times 2. These 2 hours have to be converted into seconds. So you have 60 minutes in 1 hour times 60. For us to have that time. So what do we get there? Something to do, check. So you have 2 times 5 times 60 times 60. So you get 36,000, right? Coulombs, right? 36,000 coulombs. Now, so this is what gas will, how much hydrogen gas will it produce? That's what we are looking for. But from this statement, you need 2 moles. But each mole is 96,500. So with 2 moles, you get 1 mole of hydrogen gas. So 2 times 965. Remember where this comes from? Don't forget this. 1 mole of electrons has this charge. But here we have 2 moles of electrons. That's why I'm multiplying it with 2. So this amount of charge is giving us 1 mole of hydrogen gas. Okay, 1 mole of hydrogen gas. So what about this one here? That is 3,6 coulombs will give us what? We don't know. So if you cross multiply, that x will be 36 divided by 2 times 965, like that. So these will be the number of moles. So what number of moles do we have? So 2 times 96500. You get that. So you basically have 3 zeros, right? What do you have up? 36 divided by 9 with the 3 zeros. This gives you 0.18 right? Moles. That's moles. So remember, 1 mole occupies 22.4 liters. So what about 0.186 moles? What will it give you? So that x is equal to this, that you get 22.4 times 0.186. So let's see what we get. Times 22.4. We get 4.18 liters. Okay, that's what you basically get. I hope that is very clear and straightforward, right? So let's try this also. A current calculate the quantity of electricity required to deposit 1 mole of aluminium from a solution of aluminium chloride. Hey, we don't see the current, we don't see what. Don't worry. Just remember the principles about charges. Just remember that. But let's first see how aluminium gets deposited. Aluminium ions have a charge of +3. Okay? For it to get deposited, you will have it being reduced. Okay? It will be reduced by having 3 electrons, so that you form this solid. That is what happens. That means that you need 3 moles of electrons to deposit 1 mole of aluminium. But remember that 1 mole of electrons has a charge of 6 coulombs, right? So what if you have 3 moles, like in this case here? If you have 3 moles, it will be this times 3, and those will actually deposit 1 mole just from that equation, just like what you see. So let's calculate that and see what it brings us to. So you have 965 times 3. Okay, you need 289,500 coulombs for 1 mole of aluminium. Okay, yeah. And then we have this. This one is similar to the first one, I think. So let's go through it very fast and see. Okay. You have Q equal to IT. You have 6.2 times the time. You put it in seconds, and then you get 1. So the rule is first get the moles. First get the moles. So 6.2 times 10 times that, you get 372 coulombs, right? Yes. So this current here, how many moles will it? How many moles of electrons of copper will it deposit? That's what you don't know. But if you were to look at the equation, the copper ions, for the depositing to really happen, you have that. That is what happens. So you need 2 moles of electrons to deposit 1 mole of copper, right? So you are having 2 times 96500, giving you the coulombs, the quantity of charge on the electrons of copper. Okay, so this one will give you, I think we already know this figure already. We know it already. Okay, so that is what this gives us. So let us determine the moles there. So let's so this one here gives us 1 mole, and then this one that we don't know how many moles will it give us. We don't know, right? So the moles will be equal to 3,720 divided by 193, the 3 zeros. How many moles are there? But we already know that 1 mole of copper. 1 mole of copper is equal to 64. What about these ones here? What will they give us? You cross multiply, and you get X equal to 64 times 0.009. So this one times 64, I get 1.23. These are grams. So this will give us this. Okay? Yeah, so that marks the end of this exercise of calculating numbers, electricity, coulomb, and things like that. But the rules are basically simple. Just understand the principles, the calculations will be very, very obvious. Understand the charge that is on 1 mole of electrons. Understand how to write those half equations, because they will give you the charge, then they will give you the number of moles of electrons, and then you can be able to play around with them. You need to practice these calculations as much as you can for you to grasp the concepts. Thank you for listening.